Good afternoon, everyone. I'm Hoda from University of Oklahoma. I'm a data scientist at Data Services. Prior to this role, I was a civil engineer working in Seattle, so it's really nice to be back. Today, I'm excited to share some of my work regarding building a sequence model to predict student dropout at the University of Oklahoma. I will start by motivating this research project and going through some prior publications focused on a student dropout and retention modeling. I will show you how we define this problem, a quick overview of the data set which was used to train these models, and we have some wording problem, but we'll look at some preliminary group of classifiers that I'm calling one-stage models, and then we'll compare the performance of this group against another group called a two-stage classifier, where I incorporated the sequence of courses that a student has taken prior joining our institution. And I will wrap up with some key findings. Unfortunately, student dropout is still a pressing challenge in higher education, and 40%, that percentage is coming from some published reports. 40% of undergraduate students are not able to earn a bachelor degree within their first 6 of enrollment. And it's not an easy problem to solve. Dropout is multifaceted. Economic factors, academic, social, and behavioral play an important role in a student's success. When this problem comes to transfer student, it becomes even more complex. So transfer students are those who started, the majority of them in my data set, started at a 2-year community college and then transferred to a 4-year university such as OU. These students are more likely to be working, older, and first generation. As some publications suggest, 90% of these students intend to transfer, but sadly only half will actually do, and then 1 in 10 earn a bachelor degree. This is known to be associated with something called a transfer shock. And this means that after they transfer to a 4-year university, they face some credit loss because of the articulation or some lost mapping with the credit that they earned at the previous college, and now that they can't map it to something available at our school. The other thing is the sense of belonging, self-confidence. So they have to deal with these challenges which cause them to have a dip or decrease in their performance and confidence. So I'm getting ahead of myself. Our goal was to kind of flag these at-risk students as early as possible, because dropout is not just causing them a huge financial loss, but and also the university gets a loss, like reduction in our funding. But in a broader picture, it is leading to a it's leading to a low quality workforce development, and also it questions the equity of education between native students and the transfer students. To the extent of my knowledge and literature review, the previous work on retention modeling can be grouped into 5 major approaches. Traditional approaches, usually using tree-based models like decision tree and XGBoost, and then we have more recent work using sequences of the courses at the course level or at the semester level. We also have graph-based models focused on peer-to-peer interaction and social interaction using learning management systems data. And we also have multimodal models that incorporate data from various resources, such as institutional data, behavioral data, financial data. And the approach that I'm about to present is built on all of these models except the graph-based, in particular the sequence modeling and the multimodal modeling. We define our problem as a binary classification. So using the available institutional data such as academic transcripts, demographic, financial aid, housing, employment, and advising engagement, tracking if undergraduate students talk to an advisor about what kind of courses they want to take the next semester and other challenges that they are facing with. And our goal was to predict at-risk students as soon as possible within their first term after transfer, and also identify what are the major factors contributing to their dropout. We defined dropout as, so a student is retained if they have an enrollment record at 3 semesters after their first term. And the time horizon was very early, so we limited our data up to the time when the midterm grades are posted. So the model can only see up to that time. The data set includes about 680 of undergraduate transfer students to the College of Engineering. Out of this data set, 550 went to the training set, 140 to the test set, and you see the dropout of 8% in this data set. So compared to other data mining subsets, it's a very small data set, highly imbalanced, that adds a layer of complexity and challenge to the modeling. These are the major type of features that I used or I had access to their raw data. And within each group, the variables in that group is listed, ranging from demographic, financial, academic entry, academic preparedness, first-term course load, previous institution, prior academic performance, and educational pathway. I need to emphasize that in the first round of modeling, I only used summary-based prior academic performance. So it only includes about an average GPA hour and average GPA that they brought in at the time of admission. Here, we're looking at the distribution of labels throughout these 8 semesters. I forgot to say that the data spans 4 years, from 2021 to 2024, for fall and spring semesters. One is marking the dropout students, and the blue are those who were retained. And as you see, it varies by fall and spring semesters. It also shows that it is highly imbalanced. Beside the class imbalance issue, we had to deal with some of the features that were not very informative, noisy, and inconsistent. Developmental math was one of them. On the x-axis, you see that some of them are marked with N and Y. Y are subgroups of those students who took the developmental math. And we don't have any count of dropouts in there, so this was a very low signal, not usable. On the other hand, we have the full-time indicator that shows how many of the students were enrolled with a workload of 12 hours and more, and how many were enrolled with a less than 12 hours with a 0 on the x-axis. And this signal was strong because we see persistently the percentage of dropout being higher in the non-full-time subgroup compared to the full-time. And it suggests that this signal carries a lot of information. Here is a distribution of a numerical feature called cumulative GPA, trans GPA hours. One of the interesting things is that the distribution is changing over terms, so it's time dependent. It also has some gaps and outliers that which made me to bin this numerical feature into some categorical. We are looking at the correlation between those features and the dropout label. The important thing in this plot is that these coefficient features are in a moderate range, so we have to be careful about how we are interpreting them. But the strong one is their first term credit load, which is showing a positive correlation with the label. And then we have a negative correlation between the full-time indicator and an excellent GPA, which says that a student who comes and take a 12 hours or more of credit course on their first term and they have a good historical GPA are more likely to stay. So we also see some of the historical GPA bins that I created showing up among the key features. So the classification pipeline is simple. We start with data preparation, moving on to the training and validation, and then we iterate that process until we get to an acceptable performance. And then when everybody is ready and everybody is happy, we get the permission to deploy the model and make some predictions for some future student, like the current students or someone who's coming in the next fall. To treat the imbalance problem, I used 3 balancing treatment or imbalance handling techniques, such as SMOTE, which creates some synthetic data in the minority class, or undersampling the majority class, which was my retained students, or we can assign higher importance to the minority class. So the algorithm will treat both records with the same importance. It's not biased. And then here is the first round. And as you see, the matrix show a moderate performance. It's not something exciting. Precision is about 40%, below 40%. The recall was below 50%. And I need to mention that I tried 3 or 4 different algorithms, such as logistic regression, decision tree forest, random forest, and XGBoost, with a different combination of these imbalance handling. So this model is not ready yet to be deployed. So we had 2 options: wait to get more data from coming semesters, which would extend the timing of this project, or see if we can extract more information from what we already have in hand, and we kind of ignored. So the part that I personally ignored was all the history behind this student. It just got lumped into an average GPA. So I started looking at one little thing about it is that I also look at the importance of each of those feature groups that I showed you earlier through a feature ablation process. And again, if you are not familiar with this process, it compares a model which was trained on a full set of features with another model when we remove these feature groups one by one, and then we compare these two models and see if one of those important metrics, for me it was precision recall, area under the curve, drops. And if it drops, it suggests that that feature group was carrying a meaningful or a strong signal. But if it's near zero, then it has kind of a limited incremental values, such as the ones at the bottom. And to my surprise, prior academic performance, which was the GPA, historical GPA, fell at the bottom of the table. So this was unexpected. How come the GPA doesn't matter? So I used the transformer model and I started pulling the transcript of these students and making sequences of the historical records. And then I fed that the course sequence to the transformer model, and I used the dropout label to train it. After the training was done, I extracted the embedding, and then I used those embedding as new features in my old traditional models. I just wanted to know if I can get anything meaningful out of these historical record and introduce it as a new feature or a column in my data set. Here is an example of a student course history. Each row belongs to a specific course taken at a specific time. So term code is like 2023, that's a fall term. 2023-20 is a spring term. We have subject code, we have grade type. Is it a regular? Is it a repetitive? Is it a forgiveness, remedial? And then we have the grades, letter grades. Along those, we also have some numerical features such as hours and past or attempted hours. We started the sequence modeling by preparing the course history data. I had over 90 different subjects, and I grouped them into these subgroups, which helped to reduce the size of the course subject. And then using encoding, those subjects were mapped to some numbers. And then here each term was an element in that sequence, and I used a dictionary structure with those keys, as you see, and I also had to deal with the terms with no enrollment. So I added another identifier. Is that a gap term, or is that a term with enrollment? So anyway, that's the sequence model. It comes up with term 1, term 2, term 3. I went back 10 years, considering all the fall, spring, and summer terms, and then the CLS at the beginning is just the token that summarizes this whole sequence by looking at each term, and it happens inside the transformer. This is the dynamic of training inside the transformer with epochs, and you see the steady improvement as the epoch number goes up, which suggests that the model is learning some meaningful patterns. And these are the 38 out of 32 or 9 out of 32 embeddings. And these are just numbers. They're not interpretable, at least up to now, to my knowledge. And they were added as extra columns to my previous data set. And surprisingly, it improved the performance of the model. So the yellow is my old model. The orange ones are the augmented model. And you might notice that in some of them, the performance over the test, which is the dark orange is better than performance on the train, which is a common issue with small data sets such as mine. So I had only 54 samples for my dropout to train this model. And I hope if I retrain this model again, adding more data, I will see that this kind of a noise will get reduced. Here is again looking at the feature ablation, and coarse embedding is among the toppest, like doing the most or the heavy lifting in the training. This feature is appeared or to be very informative. And again, that prior academic performance is showing up at the bottom. The key features or the key findings of this study is that definitely the coarse sequence embedding matters, and I'm planning to bring some expert knowledge or domain knowledge from our Office of the Registrar and then enrollment and some other people with expertise on how the courses are getting mapped to this model, because right now that part is lacking. And alongside the course sequence, we also saw some first-term behavior or first-term characteristics, such as if they received a financial aid, if they had a full-term or full load term, or if they performed well on their midterm grades. Final insight is that a student's intent and trajectory are better captured through their sequence of course enrollment and performance pattern rather than a static summary. And this might be true for any of your projects that deals with time. Thank you, and I'm ready, or I'll be happy to answer any of your questions. Yes. Thank you. Intervene in the students. So I had a talk with one of our directors in the Life Coaching Center, and actually this project was initiated by her through some reporting requests, and a lot of these features that you see in the model were initially suggested by her through their domain expertise. And she actually recommended that we need to have that first performance, which is usually a midterm grade at this point, because I don't have access to their online learning activities, such as do they do their homework frequently, do they attend their classes or ask questions. So those online activities are not available to me. And if you can incorporate those, then you can trace them, you can heavily monitor them up to the midterm. But she believed that we are losing a lot of after their first term. Yeah. Thank you.
All right, thank you so much, Hoda.